we're going to continue walking through our demonstrations here for the next two sessions. I have a feeling we'll end up be spending most of the time getting through the demos. If we have any time at the end, maybe we can open it up to working on the exercises or some type of Q&A, beyond what we talked about here as part of the original plan, but we'll see how things go for the next two sessions. If you already filled out the evaluation during lunch, thank you for taking the time to do that and offering your feedback. If we get to the end of the session today and you feel like you would like to offer a second submission, don't hesitate to do so. While I do have a couple of questions on there, rating things and stuff like that, that's just mostly to kind of give some feedback to me for what I can do better and improve upon in the future. But if you have additional comments you want to offer and do a second submission, you are more than welcome to do so. Okay. Let's see. That's pretty much it. So let's go ahead and continue on with our exploration here of Rust. So the next demonstration that we have is we're going to take a look at probably one of the most common features in Python, which is my thing needs to be refreshed. Hold on, let me refresh your code space will time out after a little while. And I guess our lunch break was just long enough. Give it a second here to load back up. You might have to reload yours as well. Definitely make use of the code space after our session together is over, even if it's just your own exploration of Rust. I've started using the code spaces a lot for just my own day-to-day development, believe it or not, and using it in lots of classes, even in classes where the students aren't using code spaces. I'm just using one because it's so convenient to have the whole environment. It's all web-based. I even got myself a Chromebook just to make sure that it all worked awesome on the Chromebook in case anybody is joining with a Chromebook. And it works really, really well. So if you're ever thinking about just getting a really inexpensive notebook because you want to take it on a trip with you and you don't want to worry about damaging it or whatever, a Chromebook combined with code spaces, you can code wherever you want to, as long as you have an internet connection. Okay, so let's take a look here at working with lists in Python, right? So Python lists are probably one of the most heavily used features of Python. They're very, very easy to work with. We can initialize a list by simply using the square brackets. Lists in Python can contain anything. Now, if you're really using type hints and stuff with Python, then typically your list would have the same kind of element in the whole list. But if you're just working with plain old regular old-fashioned dynamic Python, you can put all different kinds of things inside of lists. In our case here, we're just going to create three colors, red, green, and blue, add it to the list. And then down here, we're going to iterate over those colors. So one of the features of a list in Python is that you can iterate over it, right? So in Python, a lot of the built-in objects are iterable. Also, when you implement your own custom classes in Python, you can do things like override dunder iter, and you can implement your own custom iterator for a custom class, and you can make your own objects iterable as well. Where we're ultimately going to see all of those ideas pop up here in Rust 2. So we have our colors, we have our list, and we print them out. If I go ahead and run this, you'll see we get our three colors listed there. Now, what would something like this look like in Rust? So first of all, in Rust, we have what's called a vector, and then I'm going to put the actual color struct on this side, or not that, color struct. There we go. Okay. All right, so in Rust, we have what's called a vector. So a vector in Rust is the same thing as a list in Python. Of course, in Rust, our vector is going to have, like a vector of colors or something like that. It's not quite as flexible, but we have a vector. Notice that I'm going to declare the variable here as mutable, so I can push colors onto it. Remember how we just learned a few moments ago that inside the impl definition for push, that first parameter is going to be that mutable self. Okay. So because that's going to be mutable, it knows that when I'm pushing the color onto the vector, it knows that I'm mutating this. Okay. If I mouse over colors here, you'll notice that it picks up vector color. And that's because even though I don't say a particular type here, where we go to mutate it, it can see the type that we're pushing on, which means it can infer the type of data that we're storing in the vector. Okay. If I came down to here, said colors push, you'll see here I get an error saying mismatched types, expected color, found integer. Now, if I took colors push 2 and moved it to the top, now I get expected integer, found color. So you can see where Rust's type system, compiling system, is basically using the rule of what I call first usage. And because the first thing I try to push onto the vector is a color, that now determines that the vector itself is a vector of colors. Does that make sense by a show of hands? How it's able to reason through that? Languages like C# and its generic system can also do similar things, but I haven't found C#'s generic system to be quite as sophisticated as the one in Rust. Rust is truly exceptional at how it's able to infer what these types are. Anyways, down here you can see that we can iterate over colors using basically the same syntax you see in Python. And that's because colors is iterable. Okay, colors is iterable. So if we go in and we run this code, you'll see we get the same output down here. Now, if I had not marked that as mutable, you can see that we get all the red squiggles. Okay. If over here, print was not marked as public, I get the red squiggle. Okay. So its compiling system is really, really good. Now, Python with type hints is also very good, but it's not as good as this. And I remember, so I teach the languages that I primarily teach would be things like Rust, Python, C#, JavaScript, TypeScript, HTML, CSS, stuff like that. Those are the languages I primarily work with on a day-to-day basis. I do some stuff with C, some stuff with Go, and a few other little languages like Zig. But that first category of languages are the ones that I regularly work with. Anyways, a couple years ago, I was teaching a class on JavaScript. Actually, it was a class on TypeScript, not JavaScript. So it was on TypeScript, which is JavaScript with static typing. And I was talking to another programmer who was a student in the class. And the programmer said to me, the reason why they liked TypeScript was they liked the fact that they could find their bugs at development time or compile time versus finding their bugs at runtime. So when you look at all the compiler checks going on here, initially they can be frustrating. But once you get the compiler checks taken care of, you can trust with pretty good certainty that your program is going to work, and it's not going to have any major problems with it in terms of managing memory and other things like that. It's generally going to work. Now your actual logic might have a problem, but in terms of the program compiling and managing system resources and all of that, it's generally going to work perfectly fine because you're catching all of these things at development time. You're not trying to catch them at runtime. The problem with catching things at runtime is what happens if you don't run the code, right? Whenever you run a program, do you execute every feature of it? Probably not. So it's better to be able to catch it this way. Okay. So there's our ability to work with the vector and to be able to add elements to it. Now, at this stage, I would have had you work on exercise 1, I believe, is where I had that set up. So exercise 1 you would work on now, but we're not going to. Actually, exercise 1 was after number 7. I take that back. So we're going to keep on just going through our demonstrations, and we'll see how much time we have at the end, and I may have you work on an exercise. But let's take a look at the command loop. So this is one of the first things that I have people code for me in a Python class. So if you were taking Introduction to Python from me, and you were going to work with your first piece of Python code, this is actually what you would create. And the reason why I would have you create this is because I need a way to receive input from the user so we can build a program that supports multiple commands. The nice thing about this code is that it covers the creation of a function. It's got some control flow. It's got some looping mechanisms, a little bit of user interactivity. It covers a bunch of different things that we would find useful in a program. Well, the while true is going to create that infinite loop. The break command is going to allow us to exit, and we type in exit. And then, of course, we have our way of getting the command. And then right now, we're just echoing that command back to the screen. What would something like this look like in Rust? So you can see it's a lot more involved than what we just did there in Python. Python hides a lot of the details from us. Python is a very, very high-level language, one of the highest level general purpose languages you'll ever come across. If you ever do get a chance to work with like some C extension programming in Python, and you can see all the different C functions that run behind the scenes just to do what you might think of as a single operation in a Python program, you'll realize just how high level Python is. Well, programming in Rust is like programming in C, except that it's memory safe. So when you're programming in Rust, largely you are kind of programming at that level you are in C. Now, Rust has a really massive standard library and crate system relative to what you really have in C. But you're operating at that lower level, so you have to handle more of those details. So for example, here, in this Python program, where I had a single statement on line 3 to handle the input, I'm going to choose to refactor that into a function just right from the start. I'm not going to try to put all of this code down here in my command loop. So if you are working with Python and you're trying to translate your program into Rust, realize that because Rust is at a lower level, you're going to be doing things like moving things to functions much more quickly because you have to implement more of the details. I'm not going to go over this function. We've already looked at it for the most part in the class, except that there is one thing I want to mention to you, and that is line 10. Observe that there is no semicolon. Every other line in Rust has a semicolon, but there's no semicolon here. When you have a line in Rust and there is no semicolon, it is an implied return statement. Now, I could put return, and I could do that, and that would be perfectly fine. The program will run. But in Rust, it is idiomatic to do that, not to include the return statement and to omit the semicolon. By a show of hands, who thinks you could get lost in the code? Like it would be easy to misunderstand that. Yeah, I have mixed thoughts on this particular feature. Like, I get it. You don't have to type out the return statement, and we should be looking at all the characters in the code, and it's kind of cool you can omit the semicolon. But I don't know. I think it's kind of hard. It's kind of easy to miss when you're looking at the source code. Nevertheless, of course, if you just put the semicolon, we should now get a compile error, which we do because we don't return anything. So the compiler is going to catch it for us if we omit that. Is that a common Lisp thing? I did not realize that. I did not know that was a common Lisp thing. Okay. I've done some Lisp coding back in college, and for a little while I tried writing some Emacs extensions or whatever in Lisp. But yeah. In Lisp, everything is an expression. That is true. Okay. Oh, very cool. Yeah. I first learned Lisp back in college when they were using it to teach AI classes. Right. So the idea was because Lisp code and data, that barrier is very blurred. You could use it for some AI stuff. And then one time I tried writing some Emacs extensions. Emacs is all built on Lisp. Okay. So let's take a look at our main function here. So we have loop, which is an infinite loop. We have our command, and now that match statement shows back up. Well, where did we see the match statement before? We saw the match statement when working with enums. Is the match statement limited, though, to enums? Not at all. I can take my command here. Notice that I'm going to convert the string command to a string slice. I want to compare the value here collected from get command. This is going to take that string object, convert it to a string slice, so I can compare it to this string slice here. This is the default. Remember, whenever you see a string literal like this in Rust, string literals are slices. String literals are slices. So if this is a string object and this is a slice, I need to convert the object to a slice. And then by converting it to a slice, I can do the comparison. Now let's run this code real quick and let's see what happens when it executes. And my command will be add. Hello. Exit. Now, I wonder, could I remove the as string? Could I come into here and say to string? All right, is it going to let me do that? Nope, it expected a pattern. Okay, so let me do this. I'm going to take that and let's do let exit command. And then I'll take exit command And let's see if I can drop that into there like that. Okay. So if I come into here, unused variable, exit command. Let's see if it'll actually work, see if it'll even run or compile for me. So we were able to compare the string, but it's not comparing our variable here as we intended. You would never use a string for that purpose. I just thought it would be fun to explore in the code. That would be the correct way to put that together. Now, what I'd like to do is before we continue on, let's come back over here to the Copilot chat. And let's ask it, how would I implement this in Rust? Okay. So Rust, or the Copilot, opted to put our prompt, do the flushing. Now notice here how it used the unwrap. So Copilot gave us back the unwrap. And remember, unwrap, if there's an error situation, is going to panic and fail. So if you're writing a real program and you really want to do that error handling correctly, unwrap is not going to be the way to do it. Okay. We have our string being read. We do the trim, and then it checks for the if statement here. Now, what I could do is come in and say, please update this code to use the match statement. I'm going to ask it to make some changes to it so I can see what the equivalent with the match would be. Ah, very nice. Okay. So that command.trim, right, this here, is assigning this to command. And then here I don't have a command to string. That's kind of weird. How come I don't have a command, as string or whatever? I'm going to copy this code real quick. And I want us to explore something. All right, I'm going to split the same file here to the right. And what I'm going to do is I'm going to just take this code, comment it out, and I'm going to drop this code down in here. Okay. And let me remove the IOs, and the rest should be fine. Okay. So what data type is this command here? Oh, it's a string slice. So what's trim returning? Oh, trim's returning a string slice. That's interesting. So if trim is returning a string slice, why am I converting it to string and then coming back into here and converting it to as string? Raise your hand if you think you understand the question I'm asking. If the code down here just uses the string slice, why is my function producing a new string here only to then convert it back to a string slice inside of function main? That's an interesting question, isn't it? Okay, I'm going to comment that code out, and let's come back into the original code that we had. And let's do this. Let's actually come into here. Let's get rid of the toString. Let's change that to be a string slice. Okay. So far, my function looks okay. It's not complaining about anything. Let's come into here. And let's get rid of that. And take a look. I now have a problem that we had before, but now I have it in the opposite direction. Remember the problem we had before with memory, where the memory was allocated in the main function, and we had to deal with the moving or the borrowing in the function that we were calling. But look at this function here. In this function here, I'm creating the string object here. So what that, I guess, would mean is this string object is owned by get command. When I say command.trim, am I returning a string object, or am I returning a slice that points to the string object? The slice. So here's the problem. Once this function goes out of scope, what happens to the string that was created here? It'll be deallocated by Rust automatically. But what does that mean? That means my string slice is going to point to something that doesn't exist anymore. It's going to be like a dangling pointer. It's like in C or C++, you deallocate the memory, but keep the pointer variable around and keep trying to use it. Everybody see the problem by a show of hands? The memory belongs to get command. It returns a slice, right? So to fix this, I'm going to say toString. And what does toString do? ToString creates a new string object, right? And guess what it does? It will create a new string and move it as part of the return. So the caller takes ownership. See how that works? So we're going to basically get this slice, turn it into a new string, return the new string object, the caller takes ownership, and then down here, in order to facilitate the comparison, I just get a slice reference to the string that I own and use that for the comparison to exit. See the beauty of it? Like once we get it kind of figured out in our mind about this idea of this code owning, this code. Hold on one second. Sorry about that. Once we get it in our mind about this function owning the data, owning the memory, or this function owning the memory, and we think about the concept of a slice and its relationship to the actual thing it's pointing to, and who owns what, and we realize that the memory allocated here gets deallocated once you leave the function, unless, of course, you move the object out, which is what's going to happen when it gets moved to here. Now, let me ask this real quick. How many people here have ever done C programming before, and you used malloc inside of a function, and you returned the pointer back to the caller, and you thought to yourself, who's going to be responsible for cleaning this memory up? Who's going to call the free function? Anybody ever thought that to themselves by a show of hands? Like, you could see how a memory leak could occur because somebody may not realize your function is allocating heap space. And so if the caller doesn't know that memory is being allocated, they won't know to free it up, somewhere else, right? This is actually one of the big problems you deal with when writing C extensions in Python. Is because when you write a C extension in Python, you have to tie back into Python's garbage collection system, which is a reference counting system. And you have to deal with all of those details. And it's very easy to make mistakes. Even when I teach that class, and I don't teach it that often, but when I teach the C extension class and we go in there and build them, even as the instructor writing the code, if I do an on-the-fly demo or whatever, it's very easy to make a mistake. And that's really the fundamental problem with C and C++. Great languages. It's just that manual management of memory in all but the simplest of cases becomes really hard to do well. Okay. Which is why languages like Java, Go, C#, JavaScript, Python all have garbage collectors. Because for the average business software developer, running into problems with that manual memory management is just, it's too much, right? If we can let the programming language or the runtime handle that for us, then that's preferred. With Rust, we can jump back into writing system level code, but have a structured, organized way of having that memory managed. Okay. Okay. All right. Is there a way to do the move out of the function without having it be part of the return expression? My answer to that is there is not. The way that the memory moves is coming in through the parameters and then out through the return statement. Now, Rust is a big language, and it's one that is constantly evolving. It is always possible that there is some technique that I'm just not aware of or I have never had to use before. So I'm going to say there isn't, but I'm going to throw in with every time I say you can't do something, I'm going to throw in that one little caveat that it is possible there's something I'm just not aware of, or something that has recently come out, or there's a technique that somebody uses that I've just never heard of before. But to my knowledge and understanding with my Rust coding that I've done, everything is done through the parameters and through the return statement, the flow through the functions. Because if you think about it, the memory management is tied to the variables, and variables are always tied to the stack frame in which they're operating in. To try to take a variable and somehow transfer ownership that wouldn't follow that natural lifetime of the variable, I think would be problematic. Yeah, I think would be problematic. Now, there are a number of heap memory types like box that you can wrap things like structs inside of to allocate on the heap instead of putting them on the stack. There are some interesting things you can do in there, but they're not necessarily ownership related so much. It's just a way of being a little more flexible in how you move data around. But remember, the ownership part is all about the variable tied to the memory and making sure that memory is being worked with responsibly. All right, let's see. We've got some other, let's see here. What I'm going to do is this. I'm going to highlight this code just like that. I'm going to come over to here and I'm going to say, not at terminal, at workspace, explain. So I'm going to use the explain command here that's available in the Copilot chat. And I'm going to ask it to explain to me why I can't use a string. Why is a string not matching in the selected code, but a string slice matches with no problems? This would be a great example of where Copilot might be able to answer a question like this. Because you can look up things about match, you can look up things about strings, but we really need an answer that's an intersection between the match and the string. Okay? So let's see what it offers to us here as an answer. In Rust, the match statement uses pattern matching, yes, which requires the patterns be of type, that's right, partial equals and copy traits. It's not using that double equals operator. It's using those traits. We haven't talked about traits yet. We'll be talking about them here shortly. But the string doesn't implement the copy trait. So you can't use it in the match pattern. You can only use it with things that implement those two traits. Traits are kind of like interfaces. They're a little different from interfaces, and there's a little more to them than what you have in interfaces. But if you come from a language like C# or Java, you could think of them as interfaces. If you're familiar with like protocols in Python through the type hinting system, they're kind of like protocols. Anyways, that's the reason why it's not doing the comparison. Whereas on the other hand, string slices are references, and they do implement the copy trait, so you can use them in match. That's the answer to the question. Cool. And look what we did with Copilot, right? With Copilot, we could get an answer that was specific to our code that wasn't working. Like I said, you could have looked up match, you could have looked up string, and that would have been fine. But we were able to get a specific answer. Who thinks that's pretty cool by a show of hands? How we could use AI in this way to help us, right? And this is what it is. It has to do with the traits. It has to do with the traits. Okay, cool. All right, hold on one second. So there is no string. It's string capital S, the whole word. That's the string object you can create and change and put stuff in. And then there's the @ string. There's no like string without the @ symbol. It's just @ string is what they call the slice. So the question was, is there a string type that doesn't have the @ symbol? And no, it's just there's the big string, and then there's the @ string, which is the slice. Okay, cool. All right, awesome. So what I'm going to, well, let's see. I'm going to take, well, let me switch this back, and then we'll continue. Cool. And I'm going to delete that. Perfect. Okay. Oh, thank you for sharing that. All right. So now let's take a look at our next example here, which is going to be called Color Tool. Okay. So here we have our Python program that has two methods for adding a color to a list and showing the colors in the list. And then down here, we have our main method where we have this command loop. You type in the command, and then you do the add color, or you do the show color. And then over here, we have the same color class that we had previously defined. So if I come over here and I run this Python file, I'll type in add, give it a color name, red, hex code, and then I'll type in show, and I get my color. If I add, and then I'll do show. So there's my list of colors being added. So now what I'm going to do is let's take a look at the equivalent Rust program over here. So I have that get input function that we were using before. I have an add color and a show color. Notice the add color has the @ mute identifier because we're going to be basically adding a color to the list of colors. So in order to do that, we have to get a mutable reference. On line 28, you can see we're just getting an immutable reference for colors. Same print operation as before. And then down here in our command loop, we now have our mutable vector of colors. And then we have our code here where we're going to go through and do our match as string. And then we have our add, show, and exit. In this case, because add color is going to be mutating, I have to put the ampersand mute. One thing that I did not like, about Rust when I first started working with it was the fact that I had to specify these things both on the function declaration, but also on the calling of the function. But now I've actually come to like this feature. Because I have to put mute here, here, and here. Oops. No matter where I look in the code, I understand how that memory is being used, that memory is going to be mutable. And so it's a little extra typing, but it makes it really super clear about what we're doing in this case with the vector. And notice I don't put mutable on everything. Like if you put mutable on something, but you don't actually mutate it, it should complain. Well, ordinarily it complains. We go to run this. It's not complaining. Ordinarily it'll complain because we're not actually calling colors here to mutate it anywhere. That's weird. Ordinarily it will complain, but I guess in that case it's not. It's all right. Anyways, I like it because you know whether it's being mutated or not in the place that you're working with it. All right, so up here, I want you to notice this vector color. Nowhere in this code down here are we ever adding a color to the list. If I were to remove this, let's see if it can still infer. Look at that. It's still able to infer the type. So if I go to run this, I'm not going to type all that out, but it was still able to infer the type from how we called it down here. Isn't that awesome? So based upon the parameter type of add color, it knows that it's a vector of colors. I didn't have to explicitly list it. Now, typically when I write my code like this, I'll go ahead and throw in the vector color. But technically, it can be omitted. And then, of course, if you want to know what it is, you can always mouse over it if the editor that you're using provides the little hints and stuff for the code. All right. Cool. Anything else I wanted to mention here? I don't think so. Any questions? I think going back to the last example with the match, I think the compiler was when it ran, it just matched it. Whatever it was going to be a match. I'm not sure why it didn't give us a complaint about that copy trait. Obviously, we had to explicitly ask about it. And it did warn us. Remember what it said? It said this is variables not being used. And that must have been because the variable did not implement the copy trait. Okay. Let's come back over here. We're going to take a look at a refactoring of color tool that we just looked at. So we're going to have a number of files here. I'm just going to go ahead and open them all. Let's start here with main. So we're going to create a class called Color Tool App. We're going to have a separate command loop class, and we're going to take Color Tool App and we're going to pass it into the command loop. And then we're going to say command loop dot run. So here's Color Tool App. This Color Tool App kind of represents like the high level abstraction of the application. The command loop represents kind of the low level UI detail of how the user interacts with the application. If you're familiar with things like the solid principles, we're using dependency inversion in that the Color Tool App does not depend, the high level abstraction Color Tool App does not depend on the low level functionality of the UI. Instead, the command loop is dependent upon the high level abstraction. Raise your hand if you're familiar with the solid principles in dependency inversion. Yeah? Good. Okay. So here in Python, I leverage that. If I wanted to take dependency inversion one additional step, I could really introduce some type of interface, like maybe implement it as a prototype class or whatever, so that both the command loop and the higher level abstraction were dependent upon a mutual interface. But it didn't need to be that fancy for this little application. Instead, I just wanted to make sure that my higher level code wasn't dependent upon my command loop that you see here. And this command loop just has a couple of built-in commands and then calls the methods add color and show colors on this class right here. And then, of course, I've got the actual color like we had before. So what I've done here is I've separated the application from the UI, and then I pass the application into the UI, and the UI makes it accessible to the user. So if I were to come into here and run this code, it would look similar to the other stuff that we've done. And everything works as expected. Okay. So the question is, how would I go about implementing this program in Rust, right? Do things like the solid principles apply in a non-object oriented program like Rust is, right? Because usually when people talk about the solid principles and stuff, they're usually discussing those within the context of object-oriented design. So let's take a look at how we could refactor this. Okay. So let's start here with the main program. Main program looks kind of similar. Just like I now have additional Python modules, I now have additional modules here for color tool app, command loop. I'm also pulling in my crate there for color tool app and command loop. If you take a look at my main function there, I create a color tool app. That's mutable because we're going to add colors to it. I then take the app and pass it in, and then I call my command loop there. Now the question is my command loop really changing anything? If I look at my different methods here, yes, my color tool app is mutable, right? So if I come into here, if I were to remove this, let's see if that would complain. And it does, because command loop is mutable because its dependency app is also mutable. See how that works? So this mutability tracking is all the way through the hierarchy. So because app is mutable and I assign app as a data member of the command loop struct, that also makes the command loop have to be mutable because app is mutable. Everybody good with that? By a show of hands? See how that works? Okay. Now, this is where we're going to learn a really, really, really important new concept. And it has to do with lifetimes. Now, we've already been working with lifetimes. In fact, we had a great discussion just a few minutes ago in our, it was our command loop. We had a discussion about why I can't return trim, because this is created in this function. It will be destroyed inside of this function. So instead, I'm going to create a new one and return that new one back off of the trim. The lifetime of this string is the execution of this function. That's the lifetime of this string. When this function exits, this will be destroyed. Now, the string created here won't be destroyed because it's going to be returned out. And in truth, if I didn't want to trim, I could just do that. But because I want to trim and the trim returns back a slice, that's why I have to go through this process. Nevertheless, because I'm going to return a new string created here, the string here is going to be deleted from memory once I exit the function. So that is the lifetime. So look at this over here. Command loop depends on color tool app. But notice these two things are created independent of each other. I don't create the app inside of command loop. I create the app outside of command loop. But here's the problem. I need the app to last as long as the command loop does. I can't have the command loop executing and somehow app gets deleted. Rust is going to need some additional information from me in order to connect the lifetimes of these two objects together to ensure that one of them doesn't cleaned up when the other one is still needing it, to ensure the app doesn't get cleaned up when the command loop is still in need of it. Because remember, all of this memory analysis happens at compile time. At runtime, if the command is in the final compiled code to free the memory, it just frees it. It's not like a Python situation or a garbage collected language where it has some type of reference counting mechanism going on. When the compiler analyzes your code and gives you the binary, it puts the commands to free things, not based upon some kind of reference count, but based upon its understanding of where those variables are used and what their lifetimes are. So, how are we going to handle this in our how are we going to handle this in our application? And that's where these little quote A's come in. All right, let me ask you a question. Raise your hand if the moment you see the single quote A, it causes you a lot of concern. You're like, this is going to be really, really hard to figure out and understand. Okay. So the syntax is definitely tricky, but let me help you kind of understand the practical side of this. Essentially, the Rust compiler can generally figure out, based upon your code, what the various lifetimes are, and it handles it without bothering you. It just looks at your code, says, oh, this variable is going to last this long, this one's going to last this long, and it takes care of managing it all for you. However, there are times when it can't figure out what that lifetime relationship is. Can anybody tell me what happens when Rust can't figure out the lifetime relationship? What do you think is going to happen when you go to build the program? If it can't figure out the lifetime, yeah, you're going to get a compiler error. So first of all, you don't have to worry about these quote, a single quote A apostrophe A lifetimes until the compiler tells you you have to worry about it. Generally speaking, it's the compiler that's going to tell you, I don't know what the lifetime is, or we need to define the lifetime relationship between these two things. Okay. So for example, if we came into here and got rid of all of the lifetimes, we should get a compiler error, which we already get an error right there, missing lifetime specifier. If you try to come in and let's say, this is demo 12. If you try to come in and do a cargo build, it's going to complain about the lifetime parameter. So Rust, when it can't figure it out, is going to give you a compiler error. So that at least frees you up for the most part from like really worrying about it in terms of, have I forgotten to do something? Because Rust will remind you. The really hard part is knowing how to put it in there. So first of all, you want to try to understand what two things you're trying to connect together in terms of lifetime. In fact, let me go back to, we had a second ago. If you read the error here, missing lifetime specifier, expected named lifetime parameter. Okay. So you'll notice this is on the color tool app, the little app data member here within the command loop struct. When I see this code over here, and I see that it's being applied here on the command loop, what that tells me is that Rust is concerned about this object always being available when the command loop is also in memory. So to set up our lifetime parameter, we're going to come over here to the square brackets, kind of like a generic, and we're going to put the lifetime parameter A. It doesn't have to be called A. You can call it anything you want to. But I'll put apostrophe A, and I want to take this lifetime parameter, and I'm going to decorate this color tool app right here as part of the reference definition. Okay. Down here, because this is the impl, I'm going to put my lifetime thing here and move this out to here as part of the definition for the impl. And then down here, I'm going to connect that color tool app that's passed in on the new, which is then going to be assigned to here. And that connects it back to the command loop. And so that tells Rust, as long as command loop is around, that color tool app that gets passed in right here, that also has to be kept around. Now, do I have like some great little tidbit of knowledge to tell you this is exactly how you fix this every time. No. When I work on my own programs, if there's one part that I do find frustrating to work on, it takes a little bit of time, sometimes to kind of reason my way through it, it would be lifetimes. Okay. So lifetimes are typically something that happens behind the scenes, but sometimes it can't figure out from your code exactly what the lifetime of something is. And so you have to specify the additional information. The key thing is the compiler will give you an error. The lifetime parameter is set up as a generic. And then you connect the lifetime parameter to the variable declaration. In the case of a function or the attribute on the struct, so on and so forth. Okay, so that's the lifetime parameter. Definitely a little more on the intermediate to advanced side of things, but I wanted you to see what that looked like, not because I'm expecting you to go off and be an expert on lifetime parameters tomorrow, but I wanted you to see, like, we've talked a lot about ownership, borrowing, mutable, immutable, moving. We've talked a lot about a lot of different things regarding memory management. Lifetimes is this next piece on top of that, something that's ordinarily handled by the compiler, but in cases where it can't be, you have to write the code to handle that. Okay. Now, let's take a look at Color Tool app itself. So once again, Color Tool app is in its own module. There's the struct. There's the implementation. There's our console prompt. Add color with the @mute self. And then show colors. Now, if you take a look here, you'll see that there's a lowercase self and an uppercase self. This uppercase self is just referring to that particular struct right there. I can type in Color Tool app if I want to, or I can say uppercase S for self. That uppercase self refers to the struct listed here on the impl. Okay. To the struct on the impl. Can I come into, let's say, here and replace this with self? So self here is Color Tool app. And so you could also take that approach when creating a, using that new function there to create the new instance of the Color Tool app struct. All right. Well, we are upon our afternoon break now. So when we come back, we have about 5 more demos to go through. We'll take a look at the generic function. We'll take a look at a range, right? A shopping cart, and then I've got 2 little JSON file examples to look at there. I had mentioned to you that at the start of the afternoon break, I would give you the links to the survey and stuff like that. I know I gave them out at lunch, but I'll go ahead just to follow through on what I said I was going to do. I'm going to put those links in there again for anybody who'd like to fill out the survey in the final hour or so here of our time together. Like I said, your feedback is very much appreciated. I've had a number of people already fill them out. I appreciate everyone giving me different ideas and topics they're interested in. I definitely think we'll be able to do some of those in a future session. Also, too, if you have to take off before it's over, or when you're working on the exercises following today's session, definitely encourage you to join us on Discord. That's where I'll be to be able to answer questions and stuff. And other people can also help you out along the way as well. All right. With all that said, let's go ahead and take that final break, and then we'll come back. We'll come back for the final hour and 15 minutes. Thank you so much for the kind compliment. I appreciate it. It means a lot. All right. So it's 1:30 Eastern now. Let's resume at 1:45 p.m. Eastern time. We'll come back for our last hour and 15 minutes together. And by the way, we will make our way all the way through the demos, even if we have to go a little bit longer than 3 o'clock. People might have to drop off, but I'm going to walk all the way through the explanations. So we'll at least get through all the demos for today. And I appreciate everybody hanging in and asking really great questions along the way.